Ever wondered how your computer manages to process tasks so quickly? Well, the secret lies in a clever technique called caching. Picture this. You're in a library, but instead of getting up every time to fetch a book, you keep your most frequently read books at your desk. This way, you can access them quickly, without having to navigate the stacks. This is similar to what caching does in a computer system. It's like a mini memory bank that stores frequently accessed data closer to where it's needed, enhancing the overall system performance. In the world of chip multiprocessors, or CMPs, this process becomes even more fascinating, as multiple processor cores share the same cache hierarchy. This complex dance of data storage and retrieval is what keeps your system running smoothly, making tasks like browsing the web or gaming feel swift and seamless. So, how does this magical process work? Let's dive in. Modern processors usually have multiple levels of cache, namely L1, L2, and sometimes L3. These levels are organized in a hierarchical structure, with each level being larger but slower than the previous one. Let's start with the L1 cache, also known as Level 1 cache. This is the smallest and fastest cache layer. It's located directly on the processor core, allowing it to deliver data at lightning-fast speeds. In a chip multiprocessor, or CMP system, each processor core has its own L1 cache. This helps to ensure that the most frequently accessed data is readily available, eliminating the need for the core to wait on slower memory levels. Next, we have the L2, or Level 2 cache. It's larger than the L1 cache, but also a bit slower. Some CMP systems provide each processor core with its own L2 cache, while others may share a single L2 cache among multiple cores. The L2 cache acts as a bridge between the speedy L1 cache and the larger but slower L3 cache. Lastly, there is the L3 or Level 3 cache. This is the largest and slowest cache level. In CMP systems, the L3 cache is typically shared among all processor cores. This shared L3 cache allows data to be accessed by any core, even if it's not present in that core's private L1 or L2 cache. This greatly reduces the need for cores to access the much slower main memory. The hierarchical organization of these cache levels in CMP systems allows for a balanced combination of speed and size. The smaller, faster caches can quickly deliver frequently accessed data, while the larger, slower caches can store a greater amount of data for less frequent access. It's important to note that the effectiveness of this cache hierarchy heavily relies on the principle of locality in program execution. This principle states that if a data item is accessed, it's likely to be accessed again soon, temporal locality, and if a data item is accessed, items located near it are likely to be accessed soon, spatial locality. Now that we've explored cache levels, let's move on to the concept of cache coherence. Ever heard of the term cache coherence? It's all about consistency in the world of caches. In the world of chip multiprocessors, or CMPs, we have multiple processor cores sharing the same cache hierarchy. Each core might have its own set of data or instructions stored in its cache. But what happens when one core modifies its data? How do we ensure that the same data in other cores' caches don't become outdated? This is where cache coherence comes into play. In essence, cache coherence protocols are the peacekeepers of the cache world. They ensure that all caches within the system remain consistent, that they all sing the same tune, so to speak. When one core modifies data in its cache, these protocols ensure that the changes are propagated to the other core's caches, so everyone is kept in the loop. You might wonder how these protocols achieve this. Let's take a look at two of the most common ones, MESI and MOESI. Both of these are acronyms representing the states that a cache line can be in. MESI stands for Modified, Exclusive, Shared, and Invalid. MOESI adds an extra state, owned. In the modified state, the cache line has been changed and needs to be written back to main memory. In the exclusive state, the cache line is only present in the current cache. The shared state means that this cache line might also be present in other caches. The invalid state signals that the cache line is outdated. And the owned state in MOESI indicates that the cache line is modified and can be shared with other caches without writing it back to the main memory. These protocols, as complex as they might seem, are the glue that holds the cache system together. They ensure that all cores have the most recent and correct data, preventing the chaos that would ensue if each core worked with its own version of the truth. With cache coherence, we ensure all caches have the most recent data. But what about sharing data among processor cores? That brings us to our next topic, cache sharing. In a chip multiprocessor system, sharing is caring, especially when it comes to cache data. Now let's dive deeper into the concept of cache sharing. In the world of chip multiprocessors, or CMP for short, the shared cache, usually the level 3 or L3 cache, serves as a generous facilitator for data sharing among processor cores. Imagine each core as a busy worker bee. When one bee needs data that's not in its private cache, it doesn't have to fly all the way back to the main memory hive. If the data exists in the shared cache, it can fetch it from there, saving precious time and energy. This, in turn, significantly reduces memory access latency. But hold on a second. What if there's a big multi-threaded workload that's causing a traffic jam in our shared cache? Well, that's where the concept of cache partitioning comes in. In certain CMP systems, cache partitioning techniques are used to dynamically allocate cache space among processor cores. Think of it as a traffic management system for our worker bees, ensuring every bee gets its fair share of resources and space. This technique helps improve fairness among cores and isolates performance, especially when dealing with multi-threaded or multi-programmed workloads. So in essence, cache sharing is like a communal buffet table, where all processor cores can come and get the data they need. And cache partitioning is the buffet manager, ensuring that everyone gets their fair portion and one hungry core doesn't gobble up all the resources. Together, these two mechanisms work hand in hand to optimize performance in a CMP system. Each core gets to access data quickly through sharing, and no single core can hog all the cache space, thanks to partitioning. It's a delicate dance of give and take, orchestrated to perfection. Cache sharing and partitioning work hand in hand to optimize performance. But who's in charge of all these operations? Enter cache management. The operating system is like the director of a movie, orchestrating the cache's performance. Just as a director oversees every aspect of a film, the operating system plays a crucial role in cache management, which involves a few key decisions: which data to keep in the cache, when to evict data to make room for new entries, and how to handle cache misses efficiently. Let's break this down a bit. The first point is about which data to keep in the cache. This decision is primarily based on the principle of locality. This principle tells us that a program is likely to access the same data or instructions repeatedly, or data that is located near recently accessed data. By keeping frequently accessed data in the cache, the system can reduce the time it takes to fetch this data, improving overall performance. The second point concerns when to evict data to make room for new entries. This involves cache line replacement algorithms. One common algorithm is the least recently used, or LRU. As the name suggests, it replaces the least recently used data when the cache is full and needs to make room for new data. There are also other algorithms like the most recently used, or MRU, and the random replacement algorithm. The choice of algorithm can significantly impact system performance, depending on the workload's characteristics. Finally, the operating system needs to decide how to handle cache misses. A cache miss occurs when the system tries to fetch data from the cache, but the data is not there. One strategy to handle cache misses is pre-fetching, where the system predicts which data will be accessed next and loads it into the cache in advance. Another strategy is cache bypassing, where the system allows some data to bypass the cache and go straight to the main memory. This can be useful when dealing with large data that would otherwise overwhelm the cache. Managing the cache efficiently is a key to a well-performing system. Let's recap what we've learned today. It's about making smart decisions based on the principle of locality, choosing the right cache line replacement algorithm, and having effective strategies for handling cache misses. Just like a good film director, a well-managed cache can make all the difference in performance. Today, we've embarked on a journey through the world of caching in operating systems. We've delved into the intricate layers of cache levels, exploring how each one, from L1 to L3, contributes to the overall system performance. We've demystified the concept of cache coherence, unlocking the protocols that maintain data consistency across multiple caches. Further, we've navigated the shared universe of cache sharing, observing how shared caches like L3 facilitate data exchange among processor cores, and we've seen how cache partitioning techniques help to allocate cache space dynamically, fostering fairness and performance isolation. Lastly, we've looked at the critical role of the operating system in cache management, From deciding what data to cache and when, to handling cache misses efficiently. In the fast-paced world of computing, caching plays a pivotal role in keeping up the speed. Thanks for joining us on this exploration of caching in operating systems. Stay tuned for more exciting tech content.